Hi, I'm Anand Janavithla, a graduate student at Virginia Tech. Today, I'll summarize our work, learning to share autonomy across repeated interaction. Let's say you have a robotic arm that you use every day to reach for objects around the house, maybe open doors or to open a drawer, as shown here in the video. Now, the first few times you do this task, you must carefully reach for the drawer, hold on to it, and pull it open. But after you open this drawer many times, an intelligent robot should learn to assist you. So how can robots learn to assist you? This is generally formulated as a shared autonomy problem. In the current state-of-the-art shared autonomy methods, the robot is given a set of goals beforehand, and based on the human's inputs so far, the robot tries to infer the human's goal. Once the goal is inferred, the robot offers assistance proportional to its confidence in the inferred goal. This works well when the robot knows all of the human's tasks. However, what happens when the human wants to perform a new task that the robot does not know? Through this work, what we found is that instead of requiring a list of tasks a priori, robots can exploit the repeated nature of everyday tasks to assist humans complete these tasks. In the shared autonomy paradigm, during each interaction I, the robot has a task in mind Zi. While the human is performing this task, the robot observes the human's behavior. This behavior is in the form of state action pairs. Let's call a collection of these pairs as tau I. Now, as the human repeats these tasks, the robot collects a dataset D with several tau I, one for each interaction observed by the robot. Once the robot collects this dataset, it can use it to learn the human's behavior and help them. We want to emphasize that this dataset is simply a collection of previously seen behavior, and it does not require any additional assumptions about the human. So how can robots learn to help from the data collected? In our method, we identify 3 modules that the robot needs to help their human. These are recognize, replicate, and return. So first, let's talk about recognize. Consider that a human is trying to open a refrigerator door, as seen here on the left. The robot collects the state action pairs from this interaction tau I and embeds it into a latent variable Z using an encoder epsilon. Here you can think of this as a compact representation of the task at hand, or a task predictor. Once the task has been embedded, the robot can develop a policy pi. This policy maps the current state and task Z to an action that matches previous behavior. So far, what we talked about works for tasks that the robot has seen before. But what if the human is attempting a new task? Say something like reaching for a cup of coffee instead of opening a refrigerator door. Here, we do not trust the robot's assistive actions, since it's a task that the robot has not seen before. Therefore, we train a discriminator C that classifies whether the current interaction is behavior that the robot has seen before or not. So concretely, we train the following models using the data the robot has collected. The first is an encoder epsilon that uses interactions as an input and outputs the current task Z. Then we have a decoder or a policy that takes task Z and current state S as inputs to output a robot action AR. The encoder and policy pair is trained together to match the human's behavior in the dataset. Simultaneously, we train a discriminator that outputs a confidence beta on how similar the current state is to previously seen states. Together, we have an assistive action AR for the robot and a scalar confidence beta that we can use to arbitrate control between the user and the assistive action of the robot. When beta is high, the robot is confident in its assistive action and will take over. However, when beta is low, the assistive action of the robot cannot be trusted and it cedes control to the user. So now that we've seen the theory behind our approach, let's analyze it. The first thing we wanted to analyze is, do we need a separate module for task recognition? What I mean by this is, can we obtain similar performance by just training a policy on the dataset without embedding to the latent space C. To test this, we created an experimental setup as seen here on the left. We have 3 potential goals: a can of soup, a notepad, and a measuring tape. The human teleoperates the robot to reach for each of these goals, and we train our approach and an imitation learning baseline called Dagger on these interactions. Dagger directly outputs an action for a given state without embedding to the latent space C. We plot the final state error, which is how far away the robot end effector is from the desired object. Lower is better. Here we see that the final state error for Dagger after 3 and 5 repeated interactions. Contrasting with Dagger, we see that in our method, where there is a separate module for task recognition, the robot has lower final state error. This shows that instead of just averaging the human behavior, our method identifies goals and exploits that information to reach closer to the goals. In our second experiment, we consider the importance of a separate module for return. Here, a simulated human reached for a wine glass and picked it up 5 times. We compare the confidence in this previously seen task between our method, which has a dedicated module for return, and a safe imitation learning baseline called Dropout Dagger. In Dropout Dagger, the network is queried several times with the same input state, and the variance in the output action is used as a measure of the confidence. High variance implies that the model is not confident in its output, while low variance means the opposite. In this plot on the right, we see that Dropout Dagger's confidence in the task drops as the task progresses. Conversely, in our method, the discriminator maintains high confidence in the task, can offer more meaningful assistance to the user. So far, we see that our approach recognizes and assists the human in repeated tasks. But we also wanted to ensure that the robot does not resist the human or force them along a previously seen trajectory when they perform new tasks. This is especially challenging when the human is noisy. In this experiment, we consider an environment that consists of a previously seen skill, like opening the drawer, and a new unseen goal. Here, a simulated human teleoperates and opens the drawer 5 times. Our method is trained on these interactions and is unaware of the new unseen goal. At test time, we simulate humans with different levels of noise and capture the total effort required by the human to open the drawer and reach for the new unseen goal. Here we compare against the no assist baseline, where the human teleoperates the robot without any shared autonomy. Our results show that the human effort for completing the previously seen and new unseen tasks is lower for our method, even when the user is noisy. With our method working well in simulations, we decided to test it out in the physical world with actual users. The study is split into 3 parts, and in each part, users were tasked with either teaching the robot new skills or evaluating its performance on skills it's already familiar with. In part 1, users tried to reach for discrete goals that the robot had already seen before. On the left, we show a state-of-the-art shared autonomy baseline that uses Bayesian inference to infer the human's goal based on the human's actions so far and a set of goals that are given to the robot ahead of time. In the center, we show our method, which learned about these goals through user demonstrations. On the right, we plot the normalized human effort, which captures the amount of effort the human had to exert while completing the task. We see that the effort required by Bayes that requires explicit information on the goals, and our method, which learns about these goals through demonstrations, performs similarly. Next, we return to our motivating example, where users teleoperated the robot to teach it how to open a drawer. In the beginning, the robot has low confidence in the task and returned full control to the users. But through repeated interactions, the robot learned to recognize and replicate the task. Here we see some example demonstrations given by a user in the user study. On the left, you can see how the robot assists after learning this new skill. And on the right, you can see how the human effort has reduced after the robot learned to assist the human. This shows that our method can learn to assist on new skills from scratch and can reduce the effort required by the human to complete these new skills. Finally, users revisited the original tasks to see if the robot still remembers them after learning new ones. On the left, we show the robot's performance prior to learning new tasks. In the middle, we show the robot's performance after learning all new tasks. And on the right, we show the total human effort when completing the task. We see that our method learns to assist the user, thereby reducing their effort, and offers the same level of assistance even after learning new tasks. Here we show the trajectories taken by the robot when no assistance is being offered, which is shown in gray, compared against when the robot is assisting the robot. These are shown in orange. When we measured human effort across different tasks the robot had learned, we consistently see that the robot remembers how to assist users and reduces the effort required by them to finish these tasks. We also observe that the robot remembers how to assist users on previously seen tasks even after learning new ones. Overall, what we found is that when robots had prior knowledge about potential goals, our learning approach performs similarly to a shared autonomy baseline. In cases when the human repeatedly performs new tasks, our method learns to provide meaningful assistance from scratch. And finally, our method remembers how to assist users on previously seen tasks even after learning new ones. In conclusion, robots can learn to assist humans by exploiting the repeated nature of these everyday tasks while the human performs these tasks. Thank you.